Alright, welcome back again to my future self and anyone else who might be watching. Today I will be going over the end of chapter 1, and that is mainly to do with signals, time values, system calls, and library functions. So, what is a signal? In the Linux kernel, a signal is a technique that you use to let a process know that something happened. So, for example, a common signal that happens is when you press Ctrl C in the terminal, it sends a signal saying, hey, you should probably stop now. So, the signal is a way to let a program know something has happened. And an example, press Ctrl C. Sig int signal sent to program. Remember, is if a process divides by 0, it sends the signal sig fp. By 0, sig fp floating point exception. And there are 3 ways to deal with the signal. Number 1 is to simply ignore it. In some cases that's fine, but a lot of the times you do not particularly want to do that. Number 2, let the default action occur. Or number 3, provide a function. For example, the default action for most things is simply to terminate the process. But in some cases, such as with Control C, you want to give the program some time to do something before it terminates. Maybe clear the memory of different things, though usually that's done by the kernel by default. Or maybe you want it to save some important data. Now the first case here is kind of just a special case of the third one, but it is I guess an important special case since it's quite commonly used. Some more examples. Is you can do kill for the function. And I'll just calls sig kill or whatever else. Now we'll continue on to the example in okay, so we go back to the example we had of the basic shell that we had written before, and what we basically do is we add some conditions for terminating the or for sigints. So we continue to look again at the shell we had written before. You recall that Control plus C would kill the shell. However, when we run the shell, we want Control C to stop the process that is running in the shell, or if not, to just create a new line. We want it not to do this, but to kill the running process. Only. New shell with signal. So we begin as before, hashtag include appu.h, hashtag include sys/wait.h for the signals. We add static void sig int and int main void car buff max line PID T PID int status if signal sig int equals sig sys signal error. Now the main reason we do this is we do not want it to give an error when it happens. Usually this won't return an error and that'll be fine, but if it does, we want to say that there was an error and leave. For whatever reason there might be an error. Print $, now the while loop as before. Get s buff max line std in not equals null. If buff strlen buff -1 equals end of line, then buff strlen buff -1 equals null. If PID equals fork less than 0, sys fork error, else if PID equals 0, exec lp buff car star 0 ret codent execute %s buff exit 127. Now here's the parent part. If PID wait PID and status 0 less than 0, sys wait PID error print $, and exit 0, which ends the main loop. Sorry, let me make that more clear. This ends this while loop. Exit 0, finishes int main. And now here we add void sig int sig no print f interrupt $. Okay, so what's different here? Basically what happens is, as before, we import most of the functions. We also import the wait for the wait PID function. We define the SIGINT function, then underscore. We start into main void. We define our constants, and the main new line of code here is this part. This basically catches whenever the signal is generated. And what we want to happen is, if we catch a signal and it's SIGINT, then we run our predefined function here, which we elaborated here. And what we basically want is, we want to print interrupt and the same $sign we use for running the function. And then we basically continue on as before. Go to our printf, go to our while loop, and do our normal things. Most of this remains the same, completely unchanged. As a reminder, we replace the slash with the null for processing. For the exit copy function, we run a fork. We run this if child, and we run this if parent. This catches signal. And yeah, that's mainly all that's covered in this chapter on signals. We'll of course be returning them in a while. There's a lot more about signals you can learn, so we'll return that in chapter 10. Learn more in chapter 10. Which at this rate will probably be a couple of weeks. Let's continue on to look at time values. So in Unix, values are counted in seconds from time in Unix, or Unix time. Is number of seconds since epoch, which is basically 0, 0, 0, 0, 0, 1st of January 1970 at UTC. And that gives us a simple basis to compare every time to. This is stored in time underscore t. Data types. Now there is another type of time, which is process time. And this is mainly for more relative things. This is used by the CPU. Uses this. To control processes. And this is typically around 100 ticks per second. Sometimes 50 or 60 TPS. And these are stored as clock T data type. So for any process, the Unix system keeps track of three main types of process, types of values for process. These are the clock time, the user CPU time, and the system CPU time. Now these can also be divided up into things like IO time, like waiting for IO or other things, but the main thing we're looking for is for user CPU time. That's things like calculating pi or things like that. Whereas system CPU time is things like getting the Linux kernel to open some random files or checking those zip directories. So maybe a program like ls would have a lot of system CPU time because it's just checking loads of directories. So clock time or wall clock time sometimes is the full amount it takes to run. And this is divided into these two other times. User CPU time is using time used running user instructions and system time is time spent running by the kernel doing things on behalf of the process. This is things such as read, write, dot dot dot. Now, to look at this, what you can do is run some commands. cd /user/include and $time -b grep POSIX source ***h dev / no. So this just checks the POSIX source directory for any files in this format. Sorry, it's probably confusing. This will just be a backslash to say that it's continuing on to the next line because I ran out of space, and we're writing that into /dev./null, which will basically just delete it. And this will output real 0 minutes 0.81 seconds, user 0 minutes 0.11 seconds, and sys 0 minutes 0.07 seconds. Okay, I made a mistake earlier. This is not the sum of the other two times. This is just the amount of time it's been running since you started the process. Adding these two together, you see at CPU time. So total CPU time. Now the reason that is longer is because Linux kernel doesn't work on one process at a time. It might do some things, realize it has other things to do, and then come back to it later. But eventually you'll get everything done quite quickly, and it'll be fine. And note, time depends on the shell you are using. Sometimes it runs /user/bin/time. Other shells have a built-in function for time. And now we'll continue on to look at system calls and library functions. So as we mentioned at the start, all operating systems provide different ways that you can ask for services from the kernel. Services from the kernel. In Unix, there is a well-defined number of entry points, which is limited in number, and these are called system calls. Of entry points. Called system calls. Now, it is limited, but that doesn't mean there aren't a lot. So back in the day, some old Unix version 7 had around 50. Linux 3.2.0 has 380. Free BSD 8.0 has 450. And nowadays, Linux has even more. Linux 5.12, number of system calls in 5.12. You can get an entire list of them. And get a list on man7.org/linux/man pages. Man pages /man2 /syscalls.2.html. And you can see there's a lot of different ones. Simple ones such as open, or complicated ones such as pwrite v2, and anything you want to do in the kernel you can with system calls, or something that uses the system calls. In Unix, standard way is with call being a function in the standard C library. So I use a process. Calls syscall using the function. And then this invokes kernel service, and that does whatever needs to be done. So the functions aren't actually entry points into the kernel, though they may invoke one or more of the kernel system calls. So in the C standard library, most functions aren't pure system calls, e.g. printf uses write but isn't exactly the same, and not all C standard library functions need the kernel. For example, strcpy or a2i. So for most people, they don't care whether they use printf or write. It doesn't make a difference, whichever gets the job done. But if you're doing deep level things, then it does make a difference to understand that this is a system call and this isn't. So now let's look at memory allocation a bit. As an example. So malloc. In Unix, the Unix system call is sbrk2, but this is not a particularly good memory manager. That's one option. And there are other ways to work with memory in Unix. All this program does is increase or decrease the space of a process. And it takes in a value or number of bytes and changes the memory by that much if possible. You can also use a different malloc function if you want and write it yourself. Probably also most likely using the SBRK. So if you were writing a particularly performance heavy application, you could write one for yourself for your own personal needs. But other times that isn't necessary. And the graph we have here is that in the user process, we have some application code that calls on malloc, and then that calls on SBRK. It's part of the kernel. So we have a nice clean separation of duties. We have a completely almost simplistic SBRK, which does not do very much. And the specific way we want to do it is handled by malloc. Now malloc is quite a general function. Most people probably don't want to use malloc in their everyday code, but you can if you want. And if you particularly want, you can also use SBRK in your code every time you want to allocate memory. Though that'll be a lot of effort. And it's just important to realize that a lot of system calls, a lot of C standard library functions use system calls, but aren't necessarily exactly the same as the system calls. So again, you can use system calls directly, but often, for most cases, this is cumbersome. So for example, in our previous code for running a shell, we used fork exec and wait PID. And that worked fine. But in other cases, you don't particularly need to. And that's mainly the end of chapter 1. So I'll probably finish it up with a quick summary of what we covered. So today we learned that signals are a way to let a program know something has happened. We had a brief overview that there's 3 main ways you can deal with a signal, either by ignoring it, using the default action, which is usually terminating it, or providing a function that it can use. Some examples we saw were Control C, maybe there's a divide by 0 in the function, or if you use kill in PID, and that would send us a kill and kill it. We saw that we don't always want the default action to be used, and the example we used was in the shell. We want SIGINT to kill the program and return us to our normal $sign so we can run something else and not kill the shell completely as well. We looked at time values, both as Unix time and in process time. So Unix time is more everyday time, whereas process time is more of a relative measure of time, more like a stopwatch, and this is more like a regular clock. We saw that for processes, there's 3 main values. There's clock time, so the time it's been running. So you start running the program at 2 p.m. it runs for 20 minutes and then maybe pauses for 20 minutes and then runs for another 20 minutes. They'll be running for an hour, even though it wasn't running the whole time. You have total CPU time. In that case, it'd be running for about 40 minutes. And depending on what sort of task it is, it'd be split differently. If it was doing a lot of writing, copying, pasting, it'd be more system time. If it was doing a lot of number crunching, more CPU time. You look that you can use time as a terminal of a function to measure these three different values. Next, we looked at system calls and library functions and explaining a bit more about them. We learned that there are many different entry points that you can use to interact with the kernel and get it to do something for you. And mainly the way people interact with them are using the C standard library, which use a lot of system calls as part of them, but are not necessarily direct implementations. You can also use the system calls directly should you wish, or have some particular performance reasons, though in most cases they are quite cumbersome. So you have a user process, it calls a system call, and that invokes the kernel service. And we saw that printf uses write, and not all C standard library functions need system calls. We looked at memory allocation as a quick example that uses SBRK2. Though in other cases you want different memory allocation, and you can write your own form of malloc using SBRK2 if you would wish. And we looked at a quick graph that the application code invokes malloc, which invokes SBRK2, which is run in the kernel and allocates the application more memory. And we finished up there. We finished a bit early, but that's okay. So I hope to see you tomorrow. Thank you. See you.